Thank you for coming, and I'm Shakir, and I'm really excited to talk to you today about unsupervised learning and generative models. So I wanted to maybe just start with a quick question to all of you. Few people want to shout out maybe the reasons they think unsupervised learning is important in machine learning, generative models may be important, or maybe if we have someone contrarian who thinks they aren't important. Anyone wants to throw up at the back? So if you don't have enough label data to do supervised learning, that's a great one. Any other reasons or thoughts around what a generative model is, the applications while we let people settle in? Anyone else? Okay, so.
Using NLP?
Pardon?
Used in NLP?
Used in NLP, yes, to do natural language generation of text or even audio or other kinds of things. So we'll experiment and explore a lot of the different ways of generative models and unsupervised learning more generally. I think you haven't seen anything around unsupervised learning thus far in this course, but you've probably seen them in others. And so I thought we'd start with that. So what the person said at the back, why are we interested in unsupervised learning? And the first reason that many people give is to move beyond associating simply inputs to outputs of images or features to labels or to targets. But then there are other kinds of reasons, like the example that was just given around NLP, that we want to understand how the world is evolving, how it's going to change over time, and we want to be able to imagine and simulate these kind of potential evolutions of the world going forward in time. There are these things which we recognize as people that are objects in the world. They are objects like your computer, like paper, like a screen. They have certain ways in which they move, they behave, their factors of variation, as they call them, which we want to know. Related to that is we want to be able to do a more abstract kind of reasoning. And so in this kind of abstract reasoning, we want to be able to establish certain types of concepts or conceptual basis for the world and do reasoning and decision-making in that space. We want to be able to know when something is new, is interesting, is surprising. And we want to be able to generate plans about the way we will behave in the future, the way you do in reinforcement learning. So all of these are the reasons why we are interested in unsupervised learning, and I hope maybe we'll try and explore some of all of these kind of things as we go through. But unsupervised learning will just be one part of a far more bigger suite of things that you'll imagine, and under various different names, but one way to think of them are as complementary learning systems. We have several different types of learning systems: unsupervised, supervised, reinforcement learning, semi-supervised, other kinds of transductive learning that will all work together to complement each other for us to build these general purpose learning systems, right? And so when we come to generative models, I usually group their applications and their roles in three different areas. We want to have generative models because we want to build products. We want to build things which are useful, which help our everyday lives. So things like super resolution of images and video, as we want to do transmission and compression of high bandwidth data streams. We want to do text to speech, for example, to create accessibility tools. Then we want to move to areas of science. We want to continue to understand how it is that the natural and physical world observes, and then to use those scientific basis to again inform other kinds of areas like healthcare and the social world. So things like proteomics, drug discovery, understanding celestial objects, using high energy physics, where the big question in high energy physics is how we move beyond the standard model. That's what they call the current question now that we've found the Higgs boson. What is beyond that standard model? And then we have the tasks of reasoning and AI. So can we do planning? How do we do exploration as agents in the world to discover new areas? How do we build self-motivation and keep ourselves discovering new things? And maybe part of what you've seen in the other half is around doing model-based reinforcement learning. So these are all some of the different areas that I have in mind. And different products. So I'm going to do a little experiment with you, but I thought we're going to do two halves. And in this first half, I thought we'd look at 5 tricks for manipulating probabilities. And I'm going to just discuss with you 5 self-contained tools, mathematical and probabilistic tools that you can use in almost every part of machine learning, and they'll typically fall into three parts. One part will be about manipulating integrals, another part will be about manipulating densities, and another part about manipulating gradients. And these 5 tricks together, you can use them certainly for generative models, what we're going to discuss in the next part, but you have already used some of them in reinforcement learning and in other areas of machine learning that you've covered before. You've used them, and I want to just represent them to you in a different light. And then in the second part, we'll do a brief introduction to generative models. We'll look at the types of generative models that we have available, and then we'll break generative models up into 2 parts, prescribed generative models and implicit generative models, and we'll look at the different kinds of ways of doing learning in these 2 types of models. So, okay. Here are my 5 tricks, and again, I wanted to try and experiment with you because I want to try and do this again later on at the Machine Learning Summer School, so please give me feedback at the end as to how you think it worked out. So, the thing that I want to leave you in this first half of this next 50 minutes is that I want each and every one of you to be able to build a probabilistic dexterity. When you see probabilities and integrals of probabilities, you can manipulate and mold them to do the things that you need to do. And this is effectively the problem of machine learning. So if we have this probabilistic dexterity, if we have a set of tools which we can manipulate integrals, probability distributions, and their gradients, then we will have the tools to solve the fundamental problems of machine learning and AI. And some of these questions come up. One of the most fundamental questions is always to compute the evidence of a set of data. So if you have data X, you want to know what is the probability that that data set appears in the world. And knowing this quantity is, in fact, one of the most fundamental quantities you can know in machine learning, because if you know this probability X, you basically know everything. You know when it's surprising, what is probable, you know all its moments, you can do everything from there. Rewriting this evidence estimation question in a different way. So this first part is sometimes called the marginalized probability, the integrated likelihood, the partition function. It has several different kinds of names. You may want to do a simpler task than this. You may just want to compute a set of moments. This is because you want to summarize data in some way. You want to compute the quantiles or certain expectiles, and knowing those quantities and reporting them is useful. And so, for example, physics, you want to do 6 sigma computations of whether something is actually there or not. So then you'll want to do these moment computations where you'll compute an expectation of some function of a random variable. The notation is swapping around, but just use it as a general idea. Of course, the most fundamental problem in machine learning and statistics is to do parameter estimation. You want to actually know what the value of parameter theta of a model that you have is given some data X. And if you wanted to be frequentist, then you would find the point estimate and a confidence interval around theta, or if you are being Bayesian, you would find the entire probability distribution and report either its central area and then its confidence, highest probability density region. So this is probably the most common, what you've done almost in every course in machine learning so far. Then, of course, we want to do prediction, because once we have these models, we want to use it to do something useful in the world. The thing you've seen in the other part is to do planning, so that if you have a certain cost function C and an action U that you are trying to take, how is it that you can choose the set of actions U to maximize the cost under certain types of probability distribution. So this was the fundamental equation that you were all solving to target Bellman's equation and to learn the policy gradient theorem and to do value estimation as well. Then another kind of important one is, for example, if we are dealing with medical domain, you will have multiple hypotheses that we are testing, and you need to be able to compare those 2 hypotheses. Which one is better, or which one has the effect that you wanted it to have? And then the last one related to hypothesis testing is to do an experimental design. How is it that I can take an action, observe what happens in the world, and then choose the actions of the next set of experiments that I will do so that I actually learn? And so hidden in all of these things are probabilities, and these probabilities are sometimes difficult. You don't know what they are. Sometimes you are known to you partially. Sometimes you can only simulate. You don't know them analytically. In almost all of them, there is a horrible integral. It's just written 1 here, but usually it's a d-dimensional integral over the dimension of things that you're dealing with, so you can't solve it numerically. In other cases, there are gradients which need to be done through inverse probabilities, and there are other normalizing constants that appear, or in some cases, there are external factors which are affecting your model. And so in all of these cases, you will need to do some kind of manipulation, and this is where this first part is. And if we have those kind of tricks, we can manipulate all these integrals, all these gradients, all these probabilities, and then we can actually build a very rich and deep understanding of machine learning. So the first trick I wanted to present to you, you've all seen this before, it's called the identity trick. So whenever you have a problem that you have an integral or an expectation in some distribution P, you may not like that integral, you may not like P is not your friend. You can instead change the integral into an expectation under a different distribution Q. Q is something you get to choose, Q is your friend. So this is where you will use this identity trick. And so here's the expectation, you have an integral of some probability distribution x over a function f of x, right? It's the expectation of x under the distribution P. As I said, you may not like this integral for various reasons because P is difficult to compute, because f may be non-differentiable for various reasons, and you instead want to rewrite it as an expectation like this. An expectation under a new distribution Q with some transformation of the function f. So I'm just writing it as g here and writing out the integral. And so how you move between these two is to multiply your probabilities by 1. Right? So we're going to introduce a probabilistic 1, and I think you've seen this already at least in 2 different places. So let's apply this identity trick. So here's an integral problem. I want to compute the expectation of this distribution P of x given z under the distribution P of z. So that's our integral problem. And typically, if you had studied graphical models before, you would have seen this kind of latent variable problem has appeared before, right? And so the trick is to multiply this integral by 1. So I'm going to introduce this new distribution Q, and Q divided by Q is 1, so the integral is exactly the same, right? But now I can regroup the terms. I can leave P of x given z, and I can group P of z divided by Q of z as some new quantity. And actually, this ratio is something just to keep in mind. We'll look at it a bit later. And now there's a new distribution z. And now this is an integral, which is an expectation under the distribution Q of this new quantity, right? And so this trick you can use almost everywhere. And it's one of the most useful tricks. You'll use it in reinforcement learning to do sort of policy corrections. You will use it in the next slide. So there's just some things to know. Because we are dividing by Q, you need to make sure that Q is greater than 0 wherever this product of P times P is greater than 0. And Q that you are introducing and choosing must be something you should easily manipulate, right? And so this trick is obviously the basis of importance sampling that you've seen before. Where we call the ratio P divided by Q the importance weight, which is W. You can simulate or sample from Q of Z, and then you can evaluate this integral by Monte Carlo integration, right? And this is one of the most useful tools, so keep in mind this tool of integration by using Monte Carlo. And importance sampling is one of the most basic tools we have for manipulating probabilities, but it is useful only if you want to know the value of an integral, right? Because that's what importance sampling does. If you wanted to do more than know the value of an integral, if you wanted to use it for learning, then importance sampling is not going to be quite useful for you. But we'll come to that a bit later on. So you would have seen this kind of identity trick, not just in importance sampling. We will use it again later on to manipulate certain stochastic gradients. If you are doing sort of probability theory, you will always use this trick to derive certain types of bounds to show the convergence properties and asymptotic properties of the convergence. And then if you are dealing with reinforcement learning, where you're thinking of off-policy corrections, then you will always introduce these kind of ratios, which will appear to handle these kind of settings. So this is a very useful trick to have in mind. The next kind of trick is a bounding trick, and there's so many bounding tricks that I just chose the most general one to do, and I'll mention a few others at the end. But one of the most important results from convex analysis is that you can always take the function of an expectation can be bounded by the expectation of a function for functions f that are concave. Right? And this is super useful because sometimes dealing with the function of an expectation is difficult to do, and you want to swap the integral with the function that's coming up there. And of course, this is equal if the function is linear, because the expectation is linear, but for other functions, you won't have this probability. So logs are the one we will always be interested in, or most often interested in, because we want to use log probabilities for numerical reasons and for simplification of their additive property. And so we will always take the log of this integral, which is the log of an expectation, is the expectation of the log. And this will be is also used almost everywhere. You would have seen this in optimization, of course, because you're deriving what the rates of convergence of optimization algorithms are. We're going to talk about variational inference, and variational inference is derived on this quantity, and if you've studied Monte Carlo, Markov chain Monte Carlo in other courses, then you would have proven that the Monte Carlo integrators or Markov chain Monte Carlo methods can have lower variance under using Rao-Blackwell's theorem, and the crux of Rao-Blackwell's theorem is to use this form of Jensen's inequality. And there are many other ways of building kinds of bounds of probabilities this way. The other very useful one is to use Fenchel duality, another tool that we get from convex analysis. And when you can use your Fenchel dual, then you can get another bound which will always be convex and bound to probability, and then that will be useful for doing various kinds of other variational methods. Holder's inequality, which just helps you do products of probabilities into the products of the individual norms, is always useful. And many of you would have heard about optimal transport and integral probability metrics, and that's where this famous Monge-Kantarovich inequality comes in, which helps you derive yet other kinds of bounds of probabilities. And these three together, and when you put all of them together, you can build very flexible kinds of tools. So the next one is about evidence bounds. So we want to actually use this trick that we just used. So again, this is the integral problem. I want to compute the evidence p of x, which will be the integral of this likelihood function p of x given z against some distribution p of z. Now I can use this identity trick again by multiplying by q and dividing by q. And q of z was the proposal distribution in importance sampling, but here it may have a different name. We'll recreate the importance weight, so p divided by q multiplied by q. And when we did importance sampling, at this point we said we're going to solve the integral by using Monte Carlo integration, but now we're not going to solve the integral by Monte Carlo. We're instead going to apply Jensen's inequality. And so Jensen's inequality, so now do this on the log of everything, so add a log on both sides. The log of p of x will be greater than the expectation under q of the log of this quantity on the inside, right? So just read that again. Now this is an integral, an expectation over q of z of this joint log probability. And so we can just split that using the property of the log to an integral of the log probability of p of x given z minus the integral of this log ratio q of z divided by p of z. And this, of course, is a very famous lower bound. It has several names, but it will be called the evidence lower bound in this case. It's often called the variational free energy or just the variational lower bound. But we can talk about that more in the next section. But it's just the point is to know that this is now a bound on the original quantity, and knowing bounds of quantities is sometimes better than knowing the quantity itself, because you know exactly what the minimum was and you can do manipulations on this, which is easier than doing manipulations on this. And so this is where this kind of trick of using bounds comes in. And in all those previous inequalities, this is the principle that when you use Holder's inequality or when you use the Fenchel dual to create a different kind of bound, you got a new problem which is actually simpler to deal with. So I have a fourth trick, which is called the density ratio trick. And the density ratio trick is a very simple trick. There's often, like you just saw in importance sampling, there's always a ratio that appears, some ratio of two quantities. And this density ratio trick says sometimes you aren't, the naive way to compute the density ratio is to compute the top part, compute the bottom part, then do the division, and then that's why you get the number. But that's actually sometimes very difficult to do, and sometimes you aren't interested in knowing those individual quantities. You only want to know the ratio directly. So often computing the ratio is easier than computing the individual probabilities, and that's where this trick comes in. And the trick simply says that if you want to know the ratio, you can just build a classifier which will say classify samples from the distribution P star versus samples from the distribution Q star. And if you can build this classifier, then that classifier has all the information that you need to compute the ratio of P divided by Q. And in fact, you just need to do this ratio of P of coming from class P to, this is 1 minus P, so not coming from class P. I'll show you, we'll do the derivation in the next line. But this density ratio trick is also one of the most famous tricks we have in machine learning. Of course, if you've heard of generative adversarial networks, this is the core quantity or the core idea underlying generative adversarial networks. But outside, and if you go a bit wider, in machine learning, a bit outside of deep learning, then you'll find a method called noise contrastive estimation. And if you want to derive the noise contrastive estimator, this is the trick that's being used. If you've been studying Markov chain Monte Carlo methods, there's an approach called approximate Bayesian computation. And one way of doing approximate Bayesian computation is using classifiers by exploiting this trick. Some of you would have done hypothesis testing in the past, and if you want to do hypothesis testing, then one way of doing two-sample hypothesis testing is to use this kind of trick. And again, any method where you have a difference between the distribution at test time versus training time, what they call the covariate shift or calibration problem, will do that. Is there a question? Yes.
Can you explain a classifier trick again? And is it just at a specific point that you were comparing?
Okay, so let's do the derivation and then ask me this again. Are there any other questions at this point? Or let's do the derivation and then we can have a discussion around all these tricks. Okay, let's do a reminder. Here's the problem we are interested in. There's the density ratio of P divided by Q, and it's always useful to keep in mind Bayes' rule. So Bayes' rule is just a rule to do inverting probability, so to invert the probability of y given x to the probability of x given y using the ratio of the two marginals. So what we're going to do is we're going to sample data from P star and sample data from Q of x. Right? And we're going to call all the data from P star x hat and all the data from Q x tilde, and we're going to put them together into one big data set. Then, because we are manipulating the probability, we can always introduce a label. So for every data point, we are going to introduce a label and a new random variable. So we're going to introduce this random variable y. And for all the data that came from P star, we're going to give it a label +1. And for all the data that came from Q, we're going to give the label -1. So that's now enough to set up a classification or a decision problem. So there's an equivalence by doing this construction. By construction, P star of x can be written as the probability of P of x given the label y equals +1, because that's how we defined it. We said every data point that came from y must be from P and similarly from Q, and then we have this too. So now you can see the trick. We're going to do P star of x divided by Q of x can be rewritten as the ratio of these two conditional distributions, which are equivalent in all forms. Now we're going to replace. Knowing P of x given y is actually not nice to use, but Bayes' rule will help us to undo that. So we're going to do the Bayes substitution, and we're going to replace all of this with distributions of P of y given x instead. So this is where the classification is going to come in. Now I'm doing a slight assumption here. I'm assuming that the probability of P of y equals 1 is equal to the probability of P equals y equals -1. So I'm assuming there's a balanced data set, because I got to draw the samples from P and Q, but if they are not balanced, then you will actually have the ratio of the imbalance, which will be these two quantities, and then P of x and P of x is the same on both sides because the data is invariant, and those two will cancel. So then what you're left with is this class probability. It says basically to compute the ratio, you just need to know the ratio of the two class probabilities. You just need to know P of y equals 1 given x divided by P of y equals -1 given x, right? And so that is the point of this trick. It says computing a density ratio is equivalent to doing class probability estimation. And if you know the class probability estimation, then you do that. So now coming to your question at the end, the thing that answers your question is that you will do this quantity for 1x, but you will do this in expectation over the whole data set or over two different data sets. And then that's how you will use this for learning. So, okay. So that's basically this density ratio trick. And I have two last tricks, and then let's summarize and have a discussion about what these tricks mean. So that was about manipulating densities, and now I want to go to the problem of manipulating gradients themselves. So one of the most common problems in all of machine learning, and in fact all of statistical science, whether you call it statistics, operations research, in finance, is to compute this quantity. You have an expectation of a function, and the expectation is with respect to some distribution Q, and you want to compute the gradient of this expectation, but you want to compute the gradient with respect to these parameters phi, which live in the distribution with which you're taking the expectation. So I'm just going to rewrite the integral out. It's the gradient of the integral of the distribution q with the parameters phi that we are introducing in, again, some function f. That function may have some other parameters that, for the purpose of this gradient computation, we aren't going to be interested in. And if all these were simple distributions and linear functions, and it's maybe one-dimensional, you'd be able to compute this integral very easily. But in general, you won't know this, be able to compute the integral. And if you don't know the integral, you can't compute the gradient. And that's because these are high-dimensional quantities. And because they're high-dimensional, you won't be able to do the gradient. You won't know the expectation in closed form, because typically you have nonlinear functions and very complicated non-primitive distributions. And the fact, what really makes it complicated is that the gradient you are interested in is with respect to these parameters phi. And so we're going to need to do several tricks to manipulate this, but I just wanted to point out where you would see this integral. So we're going to talk, this integral is obviously one of the key things to doing learning in generative models, so we'll see in all the problems of inference in generative models that we use. If you've already done a lot of reinforcement learning and control, and this is the key question to computing the expectation under your policy and doing policy learning in the policy gradient framework for doing reinforcement learning. In operations research, you would set up the same problem of estimating a queuing problem and then wanting to know the probability or queuing rate, and then you would get the same kind of question coming up. If you're doing Monte Carlo simulation in finance, they actually have a name for this gradient. It's some Greek alphabet, alpha, gamma, delta. It just depends which gradient you are taking. So all of finance is basically about computing this integral, and they have entire textbooks just to give us all the tricks to compute this integral. And actually in many other areas of optimization, they will call knowing this quantity or doing this kind of analysis sensitivity analysis. So it's really one of the most fundamental things that we know a lot of tricks from many other areas. So there are basically only two things you can do with an integral like this. You do some trick with f, or you do some trick with q. And basically, this is everything that you can do. There are two other tricks you can do on an integral like this, but not useful for us as machine learners because we want to build scalable, large-scale, easily codable solutions. So let's look at those two. And I'm going to call things where we manipulate f a pathwise estimator, and you'll see why we'll call it the pathwise estimator later. And we'll call things where we manipulate q a score function estimator, and you'll also see why that's the case. So the first one is based on the log derivative trick, and it's not really a trick because it's basic calculus. It says the gradient of a log is just equal to that quantity, the gradient of the quantity divided by itself, right? So the gradient of a log must be this, and you're just going to use this fact that you can jump between. So why this is important is that it takes you from gradients of a log probability to gradients of a probability. So you can just jump back and forth between these two things whenever you like. So, and that kind of manipulation is very flexible because it lets you rewrite the integrals in much more interesting ways. So it has several useful properties, which you've already seen. So if you have done a course in statistics and you know what maximum likelihood is, which you all do, then you would obviously know this key quantity, that gradient of a log probability is called the score. And the expectation of the score is always 0. And this is why we actually use it for and how you would prove this, and this is part of building this probabilistic flexibility. You'll have to derive it on paper now, but eventually you should all get to the point where you see this thing and then you see, well, oh, obviously this is true because I can replace this gradient by delta q divided by q. This q, that q will cancel. You take the gradient outside of the expectation. The integral of a distribution is 1, and the gradient of something that's 1 is 0, and that's why this thing is true, right? And this thing you have also seen if you have studied the policy gradient theorem, because this was the key thing that they used to make sure that it was sensible. And then the other interesting property of the score is that the variance of the score is called the Fisher information. And this is one of the most important quantities in all of machine learning, because this is the Cramer-Rao lower bound, which is the minimum variance estimator that you can get, is defined in terms of this quantity. And so all of the properties of maximum likelihood that we get come from using this simple trick. So let's use this trick to manipulate that first integral that we had. So here's the integral, and now it's the gradient, again, of an expectation of a function f with respect to distribution q. Now, I'm going to use the Leibniz integral rule, which means that I'm going to swap the gradient and the integral. And you can typically do that for these probabilities because they all operate in the same domain. They're all continuous, and so the kind of conditions that you need are true. And I can point you to a much more deeper paper if you actually want to see all the depths of actually why it is that you can do that. And as I said, we are going to try and manipulate this quantity Q. So what I'm going to, now the gradient goes inside, so that's why there's gradient of Q times F. I'm going to use the identity trick again, so I'm just going to multiply by 1. Now I'm going to reform this ratio of delta Q divided by Q, and then that basically, using the log derivative trick from above, means that this quantity is just the gradient of the log probability. And exactly the reason why we use identity tricks is that this now is a new expectation with respect to Q. This is an expectation under the distribution Q of this function f times the gradient of the log probability, right? And I'm going to do one more step, which is, I just said to you, the good and useful property was that the expectations of this log probability are 0. And so I can actually subtract any other quantity, some constant, any constant c, and because that constant c is independent of the parameters and the expectation of this thing is 0, it doesn't affect anything that I'm doing, but the thing that it will affect is the gradient, the variance of this quantity. And knowing the variance and controlling the variance is a whole area of statistics which is called control variate estimation, and knowing how to choose c, what the optimal c is for your particular problem is something you can design. And let me re-explain this equation to you the way you learned it in reinforcement learning. So in reinforcement learning, Q is what you called the policy, and you wanted to compute the policy gradient, which is the gradient with respect to the policy parameters, which are phi in this case. You had a reward function, which was log Q, and then you called this the reward function is f, sorry, and then you had the gradient of this log Q, which is the policy. And so then you said, things that have high reward, f, you will reinforce that gradient and then you will send it up. And things that have low reward, f, well, then you will not reinforce and then you will multiply that policy gradient. And then you also introduce this thing called c, which you called it had various names. I don't know. You just called it a baseline, I think, in reinforcement learning. But in statistics, we will call this a control variate. And then you can design this. And knowing that in reinforcement learning, you have a particular an MDP, you can design a C for your MDP. And if you were doing a finance problem where you were computing a time series of returns of a stock, then you would be able to compute a C using the kind of autoregressive model you were building for that setup. So there's lots of different names also. Some people like to call this the likelihood ratio method. I think that's a bad name, so don't ever call it that. I'm just telling you, so when you Google, you'll sometimes see this, and in some reinforcement learning textbooks, they use this terrible naming. Then, of course, you've seen reinforce algorithm, and the policy gradients are built in this exact concept. And then in other areas, like more in probabilistic inference, reinforcement learning, they would call this automated inference or sometimes black box inference, right? Because this is a kind of black box integral. And when will you want to use this kind of integral? You will use it when this function f is not differentiable, because you don't need to differentiate it. All you need to be able to do is evaluate the function f. What you need to do, though, is evaluate this expectation. So you would assume that q is something which is simple, that you can sample from. And because you want to differentiate q, you will need to be able to take its derivative. You'll need to know it analytically. So almost all problems can have this thing. So this is usually the first default way of approaching a gradient estimator. So let's do a different trick, and this one has many different names, but most common today, people call this the reparameterization trick. So every distribution can be re-expressed as a function of some other distribution, or so let's do this. So I have a distribution Q of some function of some random variable Z. This distribution Q can always be re-expressed in terms of a deterministic function with some parameters phi, which will transform another distribution, which will have some distribution epsilon, into Z. So the simplest one to do is to think of the inverse sampling theorem. You have a uniform distribution. All uniform distributions can be transformed into another distribution using the inverse CDF of the distribution you are interested in, right? And this was the first thing you learned about probabilistic sampling. And this is, if you always think in this uniform setup, you'll be able to derive the most generic form of what this trick is. But typically we use other, just slightly more, we don't use such a primitive distribution as the uniform. We use other distributions like Gaussians, betas, Bernoullis, etc. And how I like to think of that is more like a set of pipes. So you have some distribution which you start off with, which is this base distribution, P of Z, what I was calling P of epsilon here, sorry for the mix-up. And then you have two sort of things which mix into this pipe. You have some parameters mu and some parameters r, and then they get mixed up through this function r. For the case of a Gaussian, it's just mu plus r times z, and then what you get out is a new distribution instead. And knowing this pipe and knowing the configuration of the pipe is useful for the gradient, because you can follow the path of this pipe backwards. And it is this reason, because of this transformation of this variable through the path function g to get this new random variable z, that this, the trick that we're about to talk about will be called pathwise estimation or pathwise computation. And so the main point of a reparameterization trick, like every reparameterization, is just the change of variables rules for probability. And if we had more time, I would have done a whole trick just for change of variables rules and shown you in sort of how they appear in continuous and discrete spaces. But we're going to skip that today. But just know that this is the rule for the change of variables. If you have a distribution epsilon and you have some function that changes epsilon to z, like here, you can know the distribution p of z by computing this gradient and multiplying by the original thing. This is, you learned this in calculus under the change of variables, and the rule is identical when we come to it in probability. And we're going to use this trick, and just keep in mind that because we are probabilities and we must exist in a probability space where things must integrate to one and volume is never lost as a conservation property, you can always use this sort of loose notation just to say that volume of probabilities must be conserved, that pz times dz must always pe times de, and these things can be equal, and that's why you can do manipulations by substituting this for this. So let's just do the trick. A bit of a non-rigorous, weird kind of derivation, but I think it will work. So again, this is our integral problem. It is the integral of a distribution of a function f against a distribution q, and we want to know the gradients with respect to phi. And you have a known transformation, which is g, which transforms samples epsilon with parameters phi into z. Right? So we're going to do this change of variables. Now let's write this a bit slowly just so you see. Wherever you see z, you can replace z by the function g of epsilon comma phi, because that is what the substitution rule is. And then I said, well, q of z can be rewritten in terms of epsilon using this change of variables rule. So it's p of epsilon, which is the base distribution, times the derivative d epsilon over dz. And there's this gradient which is going to appear because of the change of variables rule. So I'm also going to change dz to d epsilon, and the way you do dz to d epsilon is to know that d epsilon dz is equal to g prime, and so again, this is where this volume is being preserved. Right, and then I'm going to apply the inverse function theorem on this derivative, d epsilon by dz, and that effectively is going to cancel out this derivative here, g prime. And so g prime will disappear, and then basically what you'll be left is with an expectation under p of epsilon instead, then of the function of g directly. And now, actually, the integral is over epsilon, which has nothing to do with phi, so now you are free to take the gradient directly through, and you don't have to worry about there are no conditions to check. The gradient can just go directly through the integral. And so this then is basically what is called this pathwise gradient estimator. It says that if you know change of variables for q, you can then rewrite it through this pathwise gradient estimator of epsilon under a simpler distribution, p of epsilon of the gradient of the function of the change of variables. And this is nice to do because now it's just backprop. You just can take the gradient of f through g to get to phi, right? And this is why in other papers we call this stochastic backpropagation. It's called the reparameterization trick. And for every other area of probability outside of machine learning, they will call this the pathwise estimator, pathwise gradient estimator. So where you would have seen this before is when you learned about the basics of expectation, they would have maybe mentioned this thing to you called the law of the unconscious statistician, which is if you are given a transformation, how can you compute this expectation under that transformation? And so you'll see this is the point of doing this change of variables. As I mentioned, we call this stochastic backpropagation. This idea of computing gradients is where they would call this perturbation analysis, and under perturbation analysis you can derive certain other variations of this gradient. There's the reparameterization trick, and other people have called this affine independent inference, and in fact this trick is also used in Monte Carlo sampling, but I forget the name of it. I have a reference at the end. So when should you use this kind of gradient estimator? So now you need to do it much more. You actually need to differentiate through f. So f, you need to know f, and f must be differentiable. Again, q is a distribution with a transform. You need to be able to rewrite q of z in terms of p epsilon and a deterministic function g. And so those functions can be anything. It can be the inverse CDF, which is how you'll derive the most generic form of this reparameterization trick. It can be a location scale transform like this function here for the Gaussian, or it can be any other kind of coordinate transform that you have. And then you want to make sure that this base distribution P epsilon is actually something simple and easy to sample from. Okay, so that was basically 5 tricks. We looked at the identity trick, and the identity trick was a way of rewriting an expectation from one distribution to another. This is the number one trick. It's the first thing you will probably do for almost everything. So one of the most useful things to know. Then we looked at one bounding trick based on Jensen's inequality, but building bounds is one of the most useful tricks for doing learning, and especially when you want to build very large-scale learning algorithms that go to millions and tens of thousands of parameters. The density ratio trick is a useful one because, like you saw in important sampling, like you see in reinforcement learning, like you saw in almost all the other tricks, there's always a ratio of 2 distributions that appear, and this ratio can give you knowledge of how things are. We're going to look at that. The log derivative trick basically exploits the definition of what the gradient of the log is to show the properties of log likelihood functions and score functions, which are the basis of maximum likelihood. And then we looked at reparameterization tricks, which effectively just deploy the rule for change of variables of probability in all different settings to help us derive different kinds of gradient estimators. So basically the point of this half was just to leave with you the message to sharpen your probabilistic tools, to always search for those tricks that means you can manipulate probabilities in the right way. And as these tricks show that if you manipulate them, you can actually do very interesting kind of things that transform what were difficult problems that you could only solve in 1D to things that you can work on ImageNet scale of data. Okay, so that's the end of the first half. We can take a 10-minute break or have a discussion on any questions around what we discussed in the first half. Are there any thoughts, questions, comments, confusions? No? Okay, so let's take a 10-minute break and then we'll come back and do the second part. Okay, so equipped with these 5 tricks, I want to actually talk about generative models, the topic that we're here to talk about. And I'm going to talk specifically about 2 types of models, prescribed and implicit models. This is the way I split thinking about generative model. So who wants to tell me what density estimation is? Anyone wants to volunteer an explanation? What is density estimation? No takers today? Quick guess, shout from the back. Okay, so we're going to look a little bit about density estimation. People don't talk about density estimation that much. So let's talk a bit about models. So typically you have been looking at conditional models. So when you are building a classifier, you are doing supervised learning. It is a conditional model because it is a P of Y conditioned on some other observed variable X. Right? And typically, these kind of models are called regression models or classification models, or in the most generic sense, conditional density estimation. And I'll say what density estimation is. And the other side is to not be conditional, is to do unconditional models. So that's typically what people mean when they say supervised learning. You want to learn P of X. Like someone said at the back earlier, there's no targets, there's no labels. And typically, a generative model is meant an unconditional model, but even that, is not something you should really live by. I guess the key point of this is to know that there are conditional and unconditional models, and these are the things we're going to be building, but that every probabilistic model in some form or the other is a generative model. And I'm just pointing this out, is that generative model can be an odd word to use. It can be an odd statement. It may be meaningless at some points in time, so just always think about and clarify as to what we're going to mean. So we're going to talk about generative models of particular kinds. Right, so the first thing to think about is density estimation. When you did your first thinking about statistics and probability, then you were exposed to this idea of the density of data and knowing its probability, and you did that kind of density estimation by histograms, by kernel density estimation. Then later on came PCA and factor analysis, and then mixture models came, right? So these were the basic tools of density estimation, and they were any way of learning about the probability density P of x from observed data. And all we're going to do is continue in this tradition and build richer models that are going to help us deal with really complex data. So, but a generative model can mean various different things. Many people will refer to a generative model by this word, to generate. So a model that allows us to learn a simulator of data, right? So in that case, you can simulate, you can generate, and a model that lets you do that then is a generative model. For some other people, you will talk about a model for density estimation, and that will be a generative model. So if you are learning P of x in some way, or some high dimensional P of x, then that will be it. And for other people, it will be just anything that is unsupervised will also be a generative model in some way or the other. So you can choose whichever definition that you like, but typically the characteristics that's common between all of them is that there are probabilistic models that have some form of uncertainty, some form of distribution that we're going to be manipulating. Typically, we're always going to target the distribution of the data P of x, either directly or indirectly. And the key thing, I think, that makes it a generative model, rather than just call it a classifier, is that you have very high dimensional output. So a classifier has very low dimensional output. It's 1 in binary classification, 1,000 for ImageNet, but it's not more than that. Whereas P of x or generative models are entire images, entire sequences of events, entire speech signals. So these are sort of some of the definitions. So I will always encourage people to think about machine learning as built up of 3 components. You have models, and models are the thing that you use to describe the world, that you use to describe the data that you're actually dealing with, and to describe your problem. It will put all your domain knowledge or the ways of things you think you should represent knowledge in the world, and that will be what you have in your model. Now, you also have data which came from the problem that you're thinking about, and then we have learning principles. And learning principles are those things that connect the data that you have with the model that you have specified. And you need this thing that helps you interface these two things. And so you will always have these learning principles. And then for any choice of model and for any choice of learning principle, you can then put those together to form an algorithm. And even an algorithm you can form for even the same model and the same principle of learning, you can create many different kinds of algorithms. And I think if you keep this structured point of view in mind, that is how you will see the connections, like we did in all those tricks, to every other area of statistical science, whether that is in computational neuroscience, or in probability theory, or in operations research, or even in machine learning. And that is how we will see that things are the same, used in different ways, and how we can actually learn those tricks from other fields to make our own work better. So I want to talk just a little bit about models. There are 2 types of models that we'll break them into. One are the fully observed models. So fully observed models are models that you build based on the data that you see only, right? So they introduce no unobserved variables. And so here you have an undirected graphical model with a 3-way factor. That is an unobserved graphical is a model. A Boltzmann machine is another kind of model of that form. Or you have these kind of autoregressive models, k-order autoregressive models. They are fully observed. They only build dependencies based on observed data and things that you can actually measure in the world. Then you have latent variable models, and latent variable models do the opposite of that. They introduce other variables which cannot be observed in the world, but which we can learn about based on the data that we have seen. And latent variable models are both of these are equally popular in machine learning. And under latent variable models, we'll have two different kinds of latent variable models. One will be the prescribed models. And prescribed models are models where you will decide that the observational data that you have has some kind of likelihood function. There is a noise model. And by choosing a noise model, so in this graphical model, we have a random variable z, which is unobserved, and then we have a new random variable x, which itself has some distribution that we choose. And this is a lot of knowledge that we add. We basically say that we can know something about the probability that this data x has in the world, even if it's just saying that it has Gaussian noise. That is a useful amount of knowledge, and that is the likelihood function that we write in all other areas of statistics and machine learning. And this is why these prescribed models are basically likelihood-based methods of estimation. Right? And similarly, up at the top, they are also prescribed in this sense that the observed models also use likelihood functions, and they are prescribed. But implicit models, they basically use this trick of the change of variables that we discussed earlier. They take a random variable z and transform it through some function f, and that is what they say. They say that you can simulate data instead. And so these models are sometimes called likelihood-free models. So if you're reading in biostatistics, you will often see this expression of likelihood-free estimation and likelihood-free models. So we're going to look at this, but most of the time we'll spend talking about latent variable models. So when it comes to learning principles, you now have a whole plethora of learning principles to choose from. The first ones that you exposed to were the exact methods where you did enumeration of all the probabilities using a probability table, or you learned about conjugate exponential family models where you could do things in closed form. You also did in numerical methods, numerical integration for simple one-dimensional, maybe two-dimensional integrals. You computed the integrals exactly. Other methods, like the generalized method of moments, maximum likelihood, maximum a posteriori, Laplace estimation, and so on and on and on. So many and many more being added all the time. And hopefully you would have seen at least a little bit of all of these different kinds of methods, but we will look at maximum likelihood, expectation maximization, variational methods, and I should update this list. We'll look at one other thing which we'll just generically call non-maximum likelihood, so things which live outside this list. So now you get to choose one of your models, and you get to choose literally any one of these learning principles, and then that's how you will fuse your data in with your model, and then you will be able to build an algorithm of some sort. So this is where everything comes out. So let's go through 4 different cases so that you understand this thing. So you can take a convolutional neural network. This is a model. This model encodes the fact that we want to model images. Images have certain translational properties, and because of those invariance in translational properties, we will use convolution. So that's what goes into the model. We're going to choose to do penalized maximum likelihood. So that is maximum likelihood with penalty, ridge regression, methods, or map estimation, which is core. And then you get to build an algorithm in various different ways. You get to choose what kind of optimization that you get. Are you going to use some precondition optimizer? Are you going to use some stochastic optimizer? Are you going to use a batch method like BFGS? You can choose what kind of penalization you will use, whether it's L2, L1, what other kinds of regularization you will add. And all of these will build very different kinds of algorithms that you will test, and this is the thing that you're doing sweeps over when you're doing experiments. Let's look at this one, which we won't talk about today. You have the restricted Boltzmann machine, which is a latent variable model, and it's undirected. And you can do maximum likelihood estimation to learn the parameters which live in these arrows. And there are various different kinds of algorithms that you can create. You can solve that by doing contrastive divergence, which is based on building a Markov chain to sample the z's given x. You can do a variation of that called persistent contrastive divergence. You can do other ways of manipulating the gradients by tempering and natural gradients. And the 2 things we are going to look at today are latent variable models plus variational inference, and we can build many different algorithms. We can create a variation of the EM algorithm. We can do another algorithm called expectation propagation. We can do other simplifications called approximate message passing. More recently, we've created things called variational autoencoders. And then with the implicit generative model setting, we can do the same thing. We can use two-sample testing as our learning principle, and then we can create many different algorithms based on what we have, based on method of moments, using approximate Bayesian computation, or the way we do it in generative adversarial networks. But all of these take the same model, the same inference, and then end up with very different looking algorithms, but they're not actually that different, right? They may behave different, have different kind of use cases, but they have a lot to share with each other. So let's talk about different types of generative models. And when you want to build a generative model, there will be several design dimensions you want to think about. The thing is, like, how will you choose your model and choose your corresponding principles? You will need to think about the data that you have, whether the data is binary, whether it is real valued, whether it's some mixture of the two, whether they have some ordering involved in the data, and that data is going to affect how you will design your model. You will need to think about the dependency structure in that data. Can you assume that you just have a set of images that are all independent? Or are you dealing with the time series, in which case there is a temporal structure which you need to account for? Or are we dealing with some maps where we're modeling bird movements or forest fires, and then there's a spatial aspect that we have to deal with? You need to think about elements of the representation that we're dealing. Are those latent variables we will introduce, or unobserved variables, or dealing with the causality continuous, or are they discrete, or there's some mixed? Are they continuous time? Are they discrete time? And then the last one is often to think about the kind of dimensionality we want to deal with. Are we going to deal with parametric functions and parametric models, which means we're going to build very large functions with lots of parameters that we're going to choose by optimization? Or are we going to do some other kind of methods which are non-parametric, infinite dimensional, that will rely on the data to inform the kind of predictions or inferential questions that we ask? And then you have other kinds of things which will affect your decision making, the computational complexity, the modeling capacity that they have, whether there's bias, whether you need uncertainty, how well calibrated those models are as they represent the probability of the data that you saw, whether your model is interpretable to humans or not. All of these things matter, and there is a generative model that you can decide and design based on what your needs are. So the first kind of generative model are these fully observed models. And as I said, a fully observed model deals with the data directly, and they don't introduce any other variables other than what is observed. So here is a chain of data, and the data is just dependent only on other data points. And of course, all the arrows represent some kind of functions. And I just want to make a distinction between two different things. We call sometimes these model parameters, we'll call them global parameters. Global parameters are things which are relevant to all data points that you see. And often you will talk about local variables or local parameters, and local variables and local parameters are something which are specific to individual data points. So typically parameters theta of your model are something you learn over the whole data set, but you will learn latent variable zn for data point xn. So this is this distinction between local and global variables. And so one kind of fully observed models are Markov models. They will start with some x1 with a categorical distribution. Then you will build an autoregressive chain. We'll say x2 is a categorical distribution conditioned on x1 with some function pi, and so on and so forth until you reach xi. This is one of the the oldest model probably in all of computational thinking. People have won Nobel Prizes for building a model like this, right? And so very important and very powerful. And then you can write the joint probability as simply the product over I of P of X given all previous Fs. And depending on what you choose as F, if F allows you to do some variable order, you can build infinite dimensional or K-order autoregressive models, and you can condition these kind of models on other external quantities, and what, for example, in economics you will hear as called these NARCS models, the nonlinear autoregressive models with exogenous variables. So if you've seen those, these are all these models. But for the case that I'm thinking, or the case that many people do these days, all these functions, f or pi, are built by deep neural networks so that you can actually build and learn in a scalable way. So fully observed models have several properties. As I said, because they are fully observed, they directly encode how data points are observed in the world, which means you don't need to make too many assumptions about what's going on. Any data type can be used, whether it's discrete or continuous or even a mixed. And if you're building a directed graphical model like the graphs that I was just showing where there's an arrow of dependency, then parameter learning is going to be very simple. You can write out the log likelihood that we wrote there before, and then you just need to take simply the gradient, and that is the easiest thing you can do. You know the log likelihood exactly, and you can do that fast, and you can scale this up to very large models, and you have lots of different kinds of optimization and lots of different applications over time. But of course, there is this order which we're using things in, and so there's an order sensitivity which is coming in. And if we were dealing with directed models, then undirected models, then that's much more difficult, because parameter learning in undirected models is very difficult because we need to know the normalizing constant. It's not known as in the directed case. And generation can be very slow in either of these models because we need to go through this sequential process of simulating from the Markov chain. But when you do that, for example, one model called Pixel CNN, and it has now various kinds of instantiations thus far, can give you like really amazing unconditional samples or conditional samples in this case that really show it has learned the data and really can do amazing things. So if you want to look at sort of the space of different kinds of models, then one way to think of them would be along an axis of directed models versus undirected graphical models, and another axis of continuous variables versus discrete variables. And then you, in any quadrant that you choose, you can find a kind of fully observed model across any area of statistical science. So let's choose a good block. So here's a good one: undirected graphical models with continuous variables. For example, many of you would have studied Gaussian MRFs, which are Markov random fields, and then these are models there, and then you can learn about all the things in this, or long linear models as they're sometimes called. People don't work in this space anymore of discrete and undirected models, but Bose machines are there, Ising models, Hopfield networks, Potts models live in this case. But where most people work in this case is in the discrete and directed case, because images can be represented between 0 and 255, and so that's discrete. And you can build NAID, fully visible sigmoid belief networks, this Pixel CNN, which I just described to you. Any RNN language model that people brought fit in this category, and other models which live outside even of more the mainstream, like context tree switching, algorithms that live in this space. So it's a lot of fun models and to explore in this space. So then we'll go to the second part, which are these latent variable models. So latent variable model introduce an unobserved and what we'll call local random variable. So instead of only x, there's now another variable z, and z is something you can't measure, but z is something very powerful, because introducing z, A, helps you understand issues around the causal structure of the data and the world that you're dealing in, and it allows you to build very complex dependency structures. So you don't need to design the dependency structure by hand. You can introduce the z, integrate it out, and then it will induce a dependency structure in x, which is the thing you actually want to have. And so here's one kind of model, which is called a deep latent Gaussian model. It's a directed graphical model. It has several layers of latent variables, which are stochastic hidden layers, and then you connect them through deep networks in any way that you like. So you can sample Z3 from a Gaussian. You can sample Z2, condition on Z3 from a Gaussian with parameters mu and sigma that are functions of the previous Z, and we can create a tree, a hierarchy in this case. And then finally, we'd get to the observed data, where we choose a likelihood function, where in this case it is a Gaussian, but it can be anything. It can be Bernoulli distribution for binary data, can be a multinomial distribution if we had some form of categorical data, and it can be products for mixed kind of distributions or non-negative quantities. So latent variable models have very different properties. They have very easy sampling because you can just follow this tree, and then you can start from Z3, generate Z2, generate Z1, get the sampling. They are an easy way to include this hierarchical structure or depth into your model, and it's easy to encode the structure that you believe in the world. So for example, physicists actually do have knowledge about how they think the image of the galaxy appearing on the telescope appears, how every pixel appears, and you can put that knowledge in, build a graphical model very similar to what I just showed you in the previous slide. And you avoid this order dependency that we saw because marginalization, this integration of the latent variables, induces dependencies. And latent variables have a different interpretation if you are thinking, putting your hat on from information theory or from compression theory as a compression or representation of the data. And I guess one of the important things is that we always want to do model scoring, we want to do model comparison, we want to choose the best model for the problem that we have, and being able to compute the marginalized likelihood is what we can do in latent variable models. But what is difficult is that you need to know these latent variables Z to be able to do any of these things, and that inversion process is very hard. It can be difficult to compute the marginalized likelihood, which is why we need all the tricks from part 1. And it may not be easy to specify, because you need to know these, sort of going back to this inversion process, you may have to choose the kind of family of approximations, and that can be hard to do. But when you do that, you can build very flexible and powerful latent variable models of images, for example, and this is a model called DRAW. So we'll just quickly look at this one, but again, there are lots of different dimensions for which you can build a model. You can choose linear models versus deep models. You can choose parametric models versus non-parametric models. You can choose continuous latent variables versus discrete latent variables. And then you can build sort of lots of different models in different cases. So maybe something you haven't thought of or seen before are these deep, non-parametric, and discrete models. So there are lots of models in this case. One example are what they call cascaded Indian buffet processes, which are a sequence basically of discrete, infinite dimensional distributions over binary objects. Or if you've heard of something called the Dirichlet process, then you can build a hierarchical Dirichlet process, which is the non-parametric extension of a model called LDA that lives in that corner. Or the one we are actually going to look at today are deep parametric and continuous latent variables, nonlinear factor analysis, nonlinear Gaussian belief networks, and all these deep latent Gaussian models like VAE, the VAE algorithm, and DRAW. So we're going to look at that, but lots of other models to look at. And I just want to highlight separately from the latent variable models, which I just described to you, these implicit models. Implicit models are simulators. They transform an unobserved source of noise into data using a parameterized function f. So we saw this picture before when we looked at the pathwise gradient and the pathwise estimation. This is exactly of that form. We choose some source of noise, and then we choose a path through which to transform that noise. And because we will know f, we're going to manipulate f and use the knowledge that we have to learn its parameters and learn a generative model in this way. And again, we're going to use the change of variables, will be the central quantity that we'll exploit when we do this. And the model that most people see today is this one here, which is the generator network from DC-GAN, and which just simply starts with choosing a Gaussian latent variable, and then you create a function f, which is this deep convnet, which actually grows out an image. But the function f can literally be anything. It can be a linear function, can be a deep neural network, can be a recurrent model like an LSTM. It can be a non-parametric function like a sequence of Gaussian processes. Lots of different things you can use. Implicit models have different properties. They're also easy to sample and easy to specify because you can just write out this function f. It's very easy to compute the expectations because all you need to do is just sample from the noise and generate from the function, and then you basically can take averages over those samples. And it's very easy to exploit large-scale classifiers and convnets when you design those functions. But if you had any constraints, like these functions, if they needed to be invertible, if there were other kinds of constraints you needed to do, then optimization can be very difficult, and the invertibility may be hard to maintain. There isn't this likelihood, which seems to be an advantage, but is sometimes a disadvantage, because not having a likelihood model is what causes you to be unstable during optimization and to not learn the correct probability density. But the main reason is that you can't extend it to generic data types. If your function is continuous, the data you generate is continuous. If your function is discrete, you will generate discrete data, but well, you won't be able to handle discrete data. And it's very hard to compute the marginalization and do model scoring in this case. But again, lots of different things to consider. The one we're going to look at on this time, we're going to look at functions that operate in discrete time, but you could also easily look at these kind of implicit models, which are diffusions based in continuous time. So we're going to look at one-line sampling transformations, which we looked at in the earlier trick. Normalizing flows fits into this, which we won't discuss today, and generator networks in GANs, and volume and non-volume preserving optimizations. But you've already seen some of these if you looked at the Langevin SDE or Hamiltonian Monte Carlo or simple physical stochastic differential equations. So, okay, I want to talk about inference in prescribed models. So these are models with latent variable, with likelihood functions. So the model evidence, or the marginal likelihood, or the partition function, is the key quantity we'll be interested in, and that means we want to integrate out z to know p of x, right? And the learning principle of knowing the Bayesian model evidence is that all we want to do is, at every step of optimization, every time we look at our data, we want to make sure that this model evidence becomes maximized. We want the maximum evidence, the highest probability of data that we can possibly have, and that's why optimizing the model evidence is the principle for learning. And so that's the principle. If we have these latent variables, we want to integrate z to know p of x, and once we know p of x, we're going to maximize it to try and get to learn the best model possible. Of course, there's an integral which is very difficult to compute, so maybe some of our tricks will be useful here. And the basic idea is to transform this integral, which is an integral of an expectation of some distribution into an expectation of a distribution that we choose. And once we can choose that distribution, then we can be more flexible. Right, so we've seen that before. We use the identity trick and Jensen's inequality to derive this lower bound on the marginal likelihood. And as I said, this marginal likelihood is called the variational free energy, and is the basis of what we will call variational inference, which is one of the most popular methods for doing inference in latent variable models. And it is called the variational free energy because I chose to introduce this distribution Q, and I'm free to choose the distribution Q that allows me to best match the model likelihood. And so what I'm going to have to do here is learn something about Q, but I also have to learn what's about P, where's the model that I'm actually interested in. And as I said, it's sometimes called the evidence lower bound because it is a bound on the model or the data evidence. And I said we need to choose true, and the two tricks we used here were the identity trick and the bounding trick. So this just lets me allow you to explain in general what the variational principle is. A variational principle is just a family of methods that allows you to approximate something difficult with something simple. Right? And by being variational, that word variational, you can substitute it with the word functional. It is an optimization in a functional space, right? So here's some complicated distribution. This distribution is a density, and a density is a function, special kind of function. And so this is a variational problem because I'm going to choose an approximating class of functions, and it is variational because I'm going to try and find the best function to match that function. And you can do this directly using functional gradient descent, which is what we call the variational calculus. But we're going to try and avoid the variational calculus because we can actually parameterize these distributions through other parameters phi. And that means we can do parametric optimization or standard optimization on the parameters phi. Right? So this is in general, which is why, even though this is called variational inference, there are lots of things which are variational methods. In fact, reinforcement learning is itself a variational method because policies pi are these functions which you are doing a functional descent over. Or, there are many, all of information theory fits into this kind of thing, and building lots of other bounds lets you build variational methods. So just be flexible. There are lots of variational methods that exist out there. And we want to fit these variational parameters phi. So in variational inference, there are two terms. There's this first term, which is the log likelihood of log p of x given z. This is the model you get to choose. So this is, for example, a Gaussian distribution, in which case this is an L2 loss. And then you get a penalty term, which is going to say that this distribution Q that I have chosen should be something close to my prior pi. And this is good because this is a penalized way of doing learning, and we always want to have regularizers. And the other thing that's useful is that you didn't need to design the regularizer. Just by applying the variational principle and applying these two tricks, a likelihood, a reconstruction term appeared, but also the correct and regularization appeared. And this distribution Q that we introduced, which was when we did importance sampling, was just some generic distribution, was a proposal. Now this distribution Q has a meaning. It is a posterior distribution. It is something that tries to invert the probability. It tries to give you the probability of Z given X. So in all the slides that's here before, the notation is a bit sloppy. You should read Z given X here, and I'll try and fix them when I put that online. So again, Q of Z tries to match the true posterior, P of Z given Y. And knowing P of Z given Y is one of the useful inferential quantities. And then you have a reconstruction cost, which I talked about, and then a natural penalty, which is the mechanism for Occam's razor. Now, just some comments on this distribution Q. By having this problem, what was an ugly integral is now an optimization problem, because we can just use this as the loss function, and there are two types of parameters. There are parameters theta, which live in P, and there are parameters phi, which live in Q, and these are the two things you need to optimize. And so this is now a much easier problem to do. As I said, I've been writing Q of Z, but it actually depends on the data, and sometimes I'm using X and sometimes I'm using Y. Sorry for that. And you have easy convergence assessment, because this is a bound. Every time you do an improvement, the bound can only go in one direction. It must go up. And so you'll be able to, this is how you can actually plot while you are testing this, and then you have variational parameters of Q of Z. Okay, so the key thing here, I want to just switch to talking about this distribution Q of Z. So Q of Z was something you had to choose, and as I said, it is something that's trying to match the true posterior distribution, which is Z given X, this probability of Z given X. So what do real-world distributions, posterior distributions, look like? So here's an example that was made on MNIST in two-dimensional latent variables, and by enumeration, I'm just going to show you what the real posterior distribution for certain kinds of simple models look like. So here's a simple model. It has two latent variables. It's simple, one layer with a Gaussian output, and what is the real distribution is the gray thing. So you just need to look at the gray thing. It's the same in each panel with just the different zoom levels. And what are blue are samples from this Q distribution, which we sampled from after training this method. So you can see in some cases, you can't see because of the light, but some cases you can do really well. The blue can overlap the white really well, and you can actually learn the real distribution. And in fact, you can even learn it when it has this strong correlation structure. You can do that. But this is a model, I think, with the sigmoid nonlinearity in the network. But when you start doing other kinds of things, you get weird blobs like this, or you get, this one has a tan H. It's a surface that has a sharp thing like this and then carries on. Or you have something that looks like this, which has a period of very high mass and then a very long tail. Now, if you were to choose a Q as a Gaussian, it won't be able to learn this. Basically, it's going to struggle. And you can sort of, here it does well because you can do Gaussian-ish things, but it's cut off on the other side. And so real-world posteriors, even in simple cases, are complicated. And when we have high-dimensional data, they are even more complicated. So then we need to have ways of designing these Q distributions that are very flexible and efficient, and that is one of the ongoing areas of research. And so you basically have a spectrum of things to choose around this Q. You have on one side Q star, which is the optimal posterior distribution, which is just the result of Bayes' rule, P of X given Z times P of Z. You can never know this, because if you knew the truth, you wouldn't do any of this. So this side you can't get to. The exact opposite end is where you choose that everything is independent, what we call the fully factorized. This is the least expressive way to design a Q function, but very popular. So you can just do the product over k dimensions of individual univariate Gaussians, for example. Right? And then in between, there's a lot of different things. So this is where we want to be able to build these deep, rich distributions. And so what lives in between are things which are called structured approximations. They introduce some kind of dependency structure. So you can see ZK is dependent on some subset of all other Zs in the model. And this is where you can do a lot of things. And sometimes you'll hear people say structured mean field in the data, and other times not. So I thought we'd do a very simple example. So here's a model which has a Gaussian latent variable Z. It has a likelihood function, which I'm leaving generic, but you can assume it's a Gaussian or a Bernoulli distribution. And then I'm choosing a Q distribution, which is the product of univariate Gaussians, Zi given mu I and sigma I. And so what we would do is we'd write out the variational lower bound. And then we would substitute in here, this KL, because it's the product over n things, actually becomes a sum of KLs for each of the individual terms. Then you can write out the KL between two Gaussians, or the KL between any two exponential family distributions is actually known in closed form. You can actually do this as an exercise for yourself to derive the KL between two distributions, and you'll see it will have a form like this. It will be a squared error reconstruction term, and then it will have some variance correction, which is based on the log variance. And then you get the log likelihood that you always expect. So if this is a Gaussian, you get an L2 error, you get the L2 loss here. So you can do lots of things to choose the Q, because even here you still, I chose this Q as this product of univariate Gaussians, but maybe that's not a good thing to do. So you can do lots of things in between. You can do mixture models, and mixture models is a very popular one, or you can just choose to build Gaussians with much more richer covariance functions. There's many papers on building rich covariance models for Gaussian distributions. You can build structured mean field, so you can build in basically an autoregressive model. So all the other models that we learned about, they can be used to design new posterior approximations, or you can create other kinds of things. These two are related auxiliary variable models or normalizing flow methods. And I have lots of references at the end for anyone who wants to look at them. So the last bit is to look at the optimization of this kind of loss function. So there are many different ways of doing the optimization. The classical way was to do what is called the variational EM algorithm, and then to do stochastic versions of that where we can subsample and use mini batches of data instead. Then more recently, what came was this idea of doubly stochastic variational inference, and I'll explain that, coupled with this idea of amortized inference, which is the one that most people use today. So in the variational problem, and in an EM algorithm, if you recall what an EM algorithm is, you're going to do an alternating optimization between model parameters theta and variational parameters phi, right? So an EM algorithm, when you write it in code, always looks as follows. You write a for loop for I equals 1 to n, then you write a function for the E step, and the E step itself has a for loop where you compute the gradient with respect to all the variational parameters phi. So E step is about expectation, and the expectation you want is about the Q distribution. So these are the distributions, the parameters of the Q distribution. And then you come to the M step, which does the optimization with respect to the model parameters, which are theta. And because this is a bound, like any EM algorithm, every time you do one setting of updating theta and phi, you improve the bound until you reach a point where you can't do that anymore. And you inherit this by using variational inference, because the variational bound is also a quantity that is convergent this way. And the idea of just to know this is that the classical idea of EM algorithm is that you have a model P and a approximate distribution Q. You go in and you do the Q step, the E step, which is to evaluate the expectation under that distribution Q. And in the classical way, you always assume you can compute this integral exactly and analytically. And if it's known to you analytically, you use that result to compute the gradient. So this is what every EM algorithm looks like. This is difficult because now we're going to have to invent thousands of new tricks just to solve this integral here. And by inventing more and more tricks, we get situations that are less and less generic and much more specialized. So in some sense, that's not the right direction to do. We want to see if we can create generic ways of doing that. And just to jump to the end, we're going to try and swap these two things using the two tricks that we had earlier. So let's talk about amortized inference and just stay at the EM algorithm a little bit more, right? So the EM algorithm, again, this is the algorithm. It has an E step for I equals 1 to n. So you go through every data point, and for every data point, you optimize this variational bound, and you solve for every data point n. You find variational parameters phi n. And you do this again for every data point. And then once you solve n optimizations and you have n sets of parameters, then you go to the M step and then you compute this average, which is an average over n data points. So the problem now is that with this E step, what you have to do is you are solving the optimization for every data point afresh. You never reuse what you just did for data point n minus 1, and you won't use what you will do for data point n plus 1. So this seems wasteful. And in some sense, you can think of this classical E-step is something that is like memoryless. It doesn't use the knowledge of other kinds of E-step computation to inform the E-step computation for data point n. And so what we want to do is remove that sort of deficiency in some sense and introduce an idea of memory. And this is where this idea of introducing what they call an inference network or a recognition model is. What we do is now we build some new model. We'll call this thing Q, and it will have a global set of parameters phi. It won't have parameters phi n for every data point. We'll have one set of parameters phi that will apply to all the data points, right? And that's the point of having these inference networks. And the parameters of Q are now no longer global per data point parameters that you have to do optimization for. They are actually a global set of parameters that are applicable to both training and test time. And the reason it's called an amortized inference is that this new set of global parameters is what you use to spread the cost of the inference over all the data points. You get to do sometimes what they call sharing statistical strength, where you use all the other data points' inference to help inform your own inference. And so the joint, and then by having this kind of inference network, you don't need to do an EM algorithm. You don't need to alternate between model parameters and variational parameters because they're only global parameters. You can do joint optimization of all of them simultaneously. Right, so the idea of inference networks, or any place where you see this element of some kind of encoder appearing, is that it gives you an efficient mechanism to learn kind of posterior distributions where you have this kind of memory component, where you can share knowledge between different data points. So let's put variational inference and amortized inference together. And so we have this approximate posterior distribution Q, which we need to design and choose. We have a reconstruction term, which is going to give us the fidelity of how well we are learning the data we see. And we have the penalty term to do Occam's razor. Now we implement a stochastic encoder-decoder system. So our model is effectively a decoder. It takes latent variable Z through some kind of model and generates data X. So it is a generative model. And then we have a recognition model or an inference network which takes data X through another set of global parameters and gives us samples from this ZQ. In fact, the two things that this model needs to do, it needs to be able to give you samples and it needs to tell you what the entropy, just what log Q is. It doesn't need to do anything else. So when you code a class for these kind of distributions, as long as the distribution can have dot sample and dot entropy or dot log prob, that's all you need to basically implement these two things. So again, as I said, the decoder is a likelihood model. The inference is now dealt with by this encoder of variational distribution. And what this also does, when you can see it, is it transforms an autoencoder, which is a deterministic function, which is not probabilistic in this way, into a generative model, because now you can actually sample from it by just sampling from Z and then generating data. Right? And so this specific combination, again, going back to that principle of machine learning that I asked you to think about, where you chose a latent variable model X, Z, and you chose a principle of inference, which is based on variational inference, and you implemented it using amortized inference with a recognition model. That thing together is an algorithm, and that algorithm is today called a variational autoencoder. Please don't call it the variational autoencoder model. A little part of me will die. So never do that. That is wrong. A VAE is an algorithm because it defines a full set of computation, a computational graph for dealing with data, learning its posterior distribution, and doing its optimization together. So never forget what the model is. It is a latent variable model, what the principle of inference is. You use variational inference. You can replace that with almost anything else that you like, and we'll do that now in the next step. And then how you put it together was by using this inference network and amortized inference, but we could have easily solved this by variational EM or Monte Carlo EM or hybrid Monte Carlo sampling or several other methods actually. So, okay, we're running out of time, so I'm just quickly going to say a little bit about the stochastic gradient estimation. Again, here's that famous problem that came where we had two tricks earlier. We need to compute the gradient of an integral of an with respect to some function, and in the EM algorithm, we had first compute the integral, then compute the gradient. And what we're going to do now is we're going to swap the gradient with the integral first. And the way we can do that swapping of the gradient and integral is to exactly use those two tricks that we had. You can either compute this gradient by the pathwise estimator using a reparameterization trick, or you use the score function estimator by applying the identity and the log derivative tricks. Right? And so you get these two ways of doing estimation. Both of them are equally valid. And what will inform your choice will be, again, how you designed your model F. So for example, if you were working computer graphics and your model, you didn't want to write a model, you actually wanted to put a renderer, a graphics renderer as the model, then you wouldn't be able to differentiate through a renderer, not in general, though they are differentiable renderers. So then the only thing you could do is to do this model. But if you were doing a more statistical approach where we were understanding the biology of the genetic tree and that we actually built that model, then we would know about F, we could differentiate, and then that would be maybe the better approach to take. So those are called doubly stochastic. So in the last 10 minutes, I just want to quickly talk about estimation by comparison and learning in implicit generative models. So in implicit generative models, you have a simulator from some data points, from some random source Z through this function f, and it can just simulate data x. And the task that you have to do is compare samples from your data model, which I'm going to call Q, with the true data distribution, which is P star. And this is a classical problem in statistics, which is called the two-sample testing problem. You have two sets of samples. You need to compare them in some way. And we want to do one step more than what statisticians we would do. We also want to do learning of our model parameters. So we're going to need to do a little bit more. And so all we need to do is find ways to compare distributions. And there are either two things you can do. You can either compute P divided by Q, and if P divided by Q is 1, that is the definition of learning, because then you've learned the data point. Or you can say P minus Q, and if P minus Q is 0, then you've also learned, right? So these are the two principles of learning involved here, and you can do both of them. And if we had an hour, we could just talk about this one slide as different ways of doing density ratio versus density difference estimation. So let's, at the high level, talk about this. Estimation by comparison always involves two steps. It's exactly like the EM algorithm before. You have a testing step or a comparison step where you're first going to find something, some tool, some trick that helps you compare one sample of data with another and to say how close it is or how different it is. And once you have that thing which tells you how close or different, that's exactly like a gradient, and then you can use that to learn. So then you can do the learning step or the adjustment step. And so here you have the hypothesis is either that the two distributions are the same or the two are different, and you're going to try and find some loss function f. As I said, you can do this by density difference methods, by looking at P minus Q, and lots of methods under maximum mean discrepancy, optimal transport, moment matching are going to fit into this category. I'm not going to talk about that today. And then you can either look at P divided by Q, which is the density ratio method, and we can do this either by class probability estimation, because we looked at that as one specific trick, but there are other methods based on Bregman divergences and F divergences that we can solve that instead. So this is sort of a general view of that landscape. So let's just look at adversarial learning. In adversarial learning, we're going to look at this ratio of P divided by Q. And based on the density ratio trick, we know that we can solve ratios like this by building classifiers instead. Our generative model will be sample from some base distribution like a Gaussian and generate this through some function f like a convnet to generate samples. And then we're going to need to do comparison. Right, and so the comparison is to build this classifier. That's what the density ratio trick is. So how do you actually compute P of y equals 1 given x? You need to build a classifier, and that's in the statistical language called building a scoring function. So you're going to build a scoring function which is going to tell you what the probability of y equals plus 1 is, and the probability of y equals minus 1 is just 1 minus that probability because they must sum to 1. And then now that you have this, you can assign a Bernoulli loss. You can say, I want data that's under Q to be seen as the negative class and data that's from P to be seen as the positive class. And that's how you'll actually learn this scoring function with that. And you can use any sort of scoring functions. You don't only need to use the Bernoulli. You can replace this with the squared loss, in which case it's called the Breyer loss. And you can replace it with several other losses. There are entire papers just on choosing scoring functions and how you can choose the best scoring function depending on the problem you have. So this kind of idea has lots of different names, and the most generic name it has been given is called unsupervised as supervised learning. And you can see that we wanted to do this unsupervised learning, and what we first had to do was build this classifier, so that is the supervised part, and that's unsupervised as supervised learning. I mentioned earlier in the approximate Bayesian computation literature, they've also had this idea of building a classifier to decide moments or ways of comparing two data points and then learning Monte Carlo samples, so that's called classifier ABC. Noise contrastive estimation is a way of doing non-maximum likelihood estimation, like all of this in this section is. And so that uses the same idea. And then adversarial learning, in particular in the way it appears in GANs, uses also exactly this principle. So we have, again, an alternating optimization between two types of parameters. You have model parameters phi and then parameters of these scoring functions d, right? And in adversarial networks, you will call this model the generator, and you will call this scoring function the discriminator because it is a classifier, and then you have to just solve the optimization between these two things. So then again, you have the comparison loss, which is solve for the parameters of the discriminator. This is the thing that tells you how close or how different these two sets of samples are. And then you have the generative loss, which says, well, based on the knowledge that I have of D, can I use that to give me a gradient? And how you actually get this gradient is by using the reparameterization trick. Okay, so that brings me to the end. The summary of today was to sort of give you some of the tools to manipulate probabilities and then use those tricks and tools to manipulate probabilities to then build all types of generative models that you could imagine, right? And we looked at different types of generative models, which were undirected models, fully observed models, models with latent variables. I asked you always to think about machine learning within this three-prong approach of thinking of models, the corresponding learning principles, and the joint idea of algorithms. And the two examples we used of that, we said was VAE was one example of a model which was a prescribed latent variable model with variational inference, which then gave us a VAE algorithm. And the other algorithm we learned about was GANs, which used implicit generative model as its model. It used this principle of two-sample testing as its principle of inference, and we put it together by building an algorithm that used the reparameterization trick to actually do the optimization. And then we spoke about lots of other things about stochastic optimization, how we can manipulate those integrals to do more scalable inference. We spoke about amortized inference and how encoders typically employ machine learning, and then how we can build lots of different complex distributions over data. There's lots more to do. Almost every one of these represents a different topic for research, whether it is the loss function itself, whether it is how you build these Q distributions, other ways of computing gradient estimators, understanding their variance properties, what are other ways of doing non-maximum likelihood learning. All of these represent a place of more research which needs to be done, and I hope lots of you will join us in that effort. So thank you for your attention. Thank you.